This video is for AP Calculus AB, Unit 4, Day 2. This is, of course, for our snow day that we have on Wednesday. So we'll start off with our review questions here. And you can see that on number 2, you've got calculator active, but the other two are not. Just take a few minutes, please try all these, and then pause the video and try these, and then I'll show you some answers, and I'll try my best to explain how I got what I got. All right, so here are some answers for numbers 1 and 2 from the review. And number 1 is kind of a tricky little limit question. It's the limit of a composite function. And so what you want to do first, I'll actually add something to this solution here. So I'm going to say that if I'm looking at completing this, the first thing I want to do is I want to find the limit as x approaches 2 of g of x. And so as x approaches 2 on g of x, of course, we are approaching 3, right? But is it 3 from the right or 3 from the left or 3 from kind of both directions? I would propose to you that it's actually 3 from the right, because as x approaches 2, the y values approach 3 from above 3 and above 3. Like if we were to look at a table of values for this g of x graph, we would see that every single value on the table is greater than 3, except right there when x equals 2. So that's why I would propose that we're actually seeing a limit value of 3 from above 3. And that's why I was able to translate that then into the limit as x approaches 3 from the right of f of x, of that outer function. So from the right, we're clearly approaching a y value of 5. Therefore, our final answer would be this right here. So a pretty tricky limit question with that composite limit and the behavior of g of x for sure. So yeah, tough one. I would say on a scale of 1 to 10 for limits, this is up there in that 8, 9, 10 range as far as challenge goes. Okay, number 2 is one of those water tank questions, a rate in, rate out. So people are entering a line at a rate of E of t. People are leaving the line at a rate of 2 people per minute. And we want to know if the number of people in line is increasing or decreasing when t equals 8. So what I have done here is let's put a box around this. I've calculated E of 8 minus 2, and I've gotten positive 0.1972, which is positive, and that means that the number of people in line is increasing when t equals 8. One thing that I want to note here that I know that I've seen plenty of times in the past, I've seen a lot of people want to do this with their net rate. They're wanting to say that it's E of t minus 2 times t instead of just E of t minus 2. And just wanted to mention why that is, why it's not this, and why it's the thing that I've got there in the green box, that expression. So the units on the 2 would be in people per minute. The units on t would be in minutes. Therefore, the overall units would just be people. We know that the units on E of t are people per minute. So people per minute minus people really doesn't make any sense at all from a unit perspective. It's got to be people per minute minus people per minute. And so if I were to get rid of this t, I'd be left with just people per minute right there. So it'd be people per minute minus people per minute, and that actually makes sense from a units perspective. Perhaps that's something we can talk about more when I see you next time. But like I said, that's a common issue that I see with a lot of students. Okay, and then lastly, number 3. My screen will cooperate. There we go. So here's number 3. This is really similar to a question we did on that video for Tuesday's snow day. Please note that the relationship here is the same as the relationship between volume and edge length. And this differential equation looks exactly the same right after we did the DDT to everything. A big difference here, of course, is that the volume is decreasing. And so in this case, I gave you a rate of change of volume instead of rate of change of edge length. And the fact that the volume is decreasing means that the rate of change of volume has to be a negative number. So I've made this a -5 instead of a +5. My freeze frame moment was here. That's why I plugged in the 1 for E. And of course I come up with this -5/3 inches per hour for my rate of change of edge length. Hope these units make sense. The edge length of a cube is simply the length of one of these edges, one of these corners, I guess you could say, of a cube. Okay, so there's number 3. That is a related rates question. So that's the newest question from the review. And like I said, really similar to the one we did in the previous video for related rates. So today, we're going to continue looking at related rates. I've got 2 examples I want to do. So I would encourage you, I know you're just still kind of beginning here with these. I would encourage you to try. See if you can get part of the way through these and get to a good place. See if you can finish it, see if you can get an answer, see if you can get a right answer. I mean, I don't know. Do your best. Pause the video, and then play the video when you're ready to see a solution. So, all right. I'll get that solution here in just a second. All right. So here's number 1. I'll read it out loud to you. It says, a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when its base is 15 feet from the wall? Okay, so the first thing we're going to do is we're going to try to mark this question up. Maybe you remember that from the previous video. Whenever you have a word question like this, we want to mark the question. So it says, how fast is the top of the ladder moving down the wall? So that's kind of the question. It's asking us, how fast is that top of the ladder moving as someone pulls the base away from the wall? So once I identify what I'm trying to find, something that comes to mind here would be perhaps a picture would be useful. So I'm going to draw a picture here. Here is the wall. Here is the floor or the ground. And here is the ladder. And I'm thinking I want to label this picture. I've got a lot of things going on. I think there's a lot of ways we could label this. I'm going to call this vertical side Y. I know that as this ladder is pulled away from the wall, Y is going to be changing. I'm going to call that X right there. You could call that a height and a base. You can call this a number of things. I choose Y and X. Y because it's a vertical measurement, X because it's horizontal. And so I feel like that's an appropriate way of labeling it. And then, of course, the ladder is going to be the same length no matter what, no matter where it is. It's 25 feet long. And so that would be my picture of this situation. Let me keep going here. As far as what I'm trying to find, it says, how fast is the top of the ladder moving down the wall? I'm going to interpret that as dy dt. That's how fast the top of the ladder is moving down the wall. And I'm going to say that that's what I'm trying to find. That's my unknown, so I just put those question marks there. And like we did yesterday, I'm going to read through the rest of the question and try to figure out if there are any other rates that are in play here. There should be at least one more. And when I look at this, I see the base of the ladder is pulled away from the wall, and there's that key word, at a rate of 2 feet per second. So somebody's pulling this ladder away from the wall. And so I'm going to say that the rate of the base being pulled away from the wall would be represented by dx dt. And this would be 2. Again, the key word there, of course, is rate. That's how I know that it's another rate. And I would interpret that as dx dt, since I labeled my base length x. Next thing I want to do is think about the freeze frame moment. The key word in identifying the freeze frame moment is, of course, when. And it says when the base is 15 feet from the wall. So I'm going to say my freeze frame moment is when x is 15. Okay, so like yesterday, one of the big challenges here is going to be to pick the relationship, the equation that relates all of these things together. And so I've got quite a bit of information. I've got a picture of a ladder leaning up against a wall. I've got a y, I've got an x, I've got a length of a ladder. And then, of course, the obvious thing is that the picture is clearly a triangle and not just a triangle. So I'm hoping that as you pondered this and thought what the relationship might be, you considered a number of things. Let me just run through a couple that it's not. Somebody might think that its area equals 1/2 BH. But if you think ahead, if I were to do DDT of this, I'd get a dA dt variable, and I have no idea what that is, and that's not what I'm trying to find, so I don't think I'd use area. Sometimes trigonometry is the way to go. Like you could maybe label this angle theta. You might say, cosine of theta equals x over 25 or something like that. So again, there's nothing wrong with that, except if I did do a derivative, a ddt here, I'd get a d theta dt term, and that is not something that I know, and that's not something that I care about. So that's not it. You might be screaming at your computer right now because you already know this. It's the Pythagorean theorem, right? This is actually the right relationship. And let's talk about why it's the right relationship. It's because when I do a ddt here, I'm going to get a dx dt, which is something that I know. I'm going to get a dy dt, which is the thing I'm trying to find. And I don't get anything extra. So I've got everything I want, nothing that I don't want. So this is the right relationship. Okay, so once I've picked out the right relationship or the right movie, to use the same kind of thought process as yesterday, I'm going to push play on my movie, and that's signified by doing DDT to everything. So this would give me 2x times dx dt plus 2y times dy dt, and then the derivative of 25 squared would just be 0. Please keep in mind that the dx dt and the dy dt are coming from a chain rule. It's really implicit differentiation, which is the chain rule. We're just doing the derivative or the ddt of the inside. Okay, so once I've pushed play, it's time to fill things in that I know. I know that my freeze frame moment is 15, so I'll plug a 15 in for x. I know that dx dt is 2. 2y, well, I don't know y for the freeze frame moment. We can figure that out. And I know that dy dt is what I'm trying to find. So how do I find the y? I will come over here to the right side. And the way that I'm going to find y is I'm going to use my Pythagorean theorem at the freeze frame moment. So I would write freeze frame moments would be 15 squared plus y squared equals 25 squared. If I square and subtract and square root and all that good stuff, I end up with y is 20. It's actually a 3, 4, 5 right triangle. And so since y is 20, I can drop that right in there for my freeze frame moment. And now I'm going to just solve for dy dt. So, of course, this is 60. That's 40. Dy dt equals 0. So I subtract 60 and divide by 40. I think I'm going to get dy dt equals negative 3 over 2. And that would be, units wise, would be feet per second. And I've got it. One question to think about just in the concept of this, I hope that it makes sense that dy dt is negative. A lot of times people will say, well, that's because the ladder is moving down. I would actually give a different reason for that. I would say that the reason why dy dt is negative is because y is decreasing in length. I hope that makes sense based on all the relationships we talked about with f prime, and f double prime. If the rate of change of y is negative, that means y is decreasing. I think we can see that as the ladder is pulled away from the wall, the y value will be decreasing, hence the rate of change of y being negative. Okay, we've got one more, and just like on this one, I would encourage you to do your best. This is a little bit of a different question. Could present some good challenges for you, but do your best to figure it out. I'd be willing to bet that you can. So try it, pause the video, try it, and then feel free to play the video to see a solution when you're ready. Okay, so this says the value of a share of stock in a new electric car company, the value being measured in dollars, is related to the price of the company's electric car by this V equals 0.9886p to the 0.1314. If the price of the car is valued at $41,468, but is dropping at a rate of $41.27 per day, at what rate is the value of the stock changing in 5 days? Okay, so just like any other word problem like this, we're going to put a box around the what do we want to find. We want to find out at what rate the value of the stock is changing. So I know that the value of the stock is represented by the letter V. So I'm going to come over here and say dV dt is what I'm trying to find. Other rates involved, I'll underline those. The price of the car is dropping at a rate of $41.27 per day. So the price of the car is represented by the letter P. So I'm going to say dP dt, and I'm going to write negative 41.27. The reason why I make that a negative number is because the price is dropping. The price is decreasing, so the associated rate would have to be a negative number. Okay, and then my freeze frame moment is in 5 days. So I'll just put when t equals 5. So this question is a little bit different than the other ones that we've looked at so far in that the relating equation is given to you. It's right here. And so what I can do is I can use that. That's going to be my movie, again, to kind of use the same kind of thought that I've used here in the past. So this is it. As far as my relationship, it relates the V and the P. So all I need to do is get going with ddt, right? I need to push play. So ddt of all this, ddt of V would be dV dt equals, and then of course this is a straight up power rule. This would definitely be a calculator active question. So go ahead, let's see if I do the power rule here. I get 0.12990204 p to the negative 0.8686, I think. Yep. And then, of course, I need to multiply by the ddt of the inside. So I'd multiply by dP dt. Okay, so I've pushed play on my movie. Now I just need to plug in the appropriate values. See how this all turns out. So I'd say dV dt at the freeze frame moment equals 0.12990204. I'll leave this blank for a minute. P to the negative 0.8686, and then dP dt I already know is negative 41.27. Okay, so the challenge here, of course, is the P at the freeze frame moment. So there's a number of things that people will try to put in here over the years. Sometimes people will try to put 5, but of course 5 is a time, and P is the price of the car, so that doesn't really make much sense. The other thing that I will see people put in here is $41,468. That makes a little bit more sense because that actually is a price of the car. But the problem with this one is this is the price of the car 5 days ago. And I want to know the price of the car now because that's my freeze frame moment. So I don't want that number. What I do want to do, I maybe come off to the side here and say, well, the price after 5 days would equal 41,468 minus 5 times 41.27, right? It's price of the car is dropping $41.27 per day. And so this ends up being $41,261.65. Okay, so that's actually the number that I want because that is the price of the car at the freeze frame moment. So that's actually what I'm going to be putting in my calculator. And this ends up being a pretty small number. So it'd be dVdt at t equals 5 is negative 5.2503 times 10 to the negative fourth. Obviously a very small number. That would be measured in dollars per day, I think. Yeah, dollars per day. And that would be the rate of change of the value of the stock based on this relationship. Okay, so I know it's weird to not be talking about this in class, but it is what it is. It's what we got to do. The good news is that we should be able to get in a couple of days here. Hopefully we'll have school on Thursday, and I know I've got more related rates planned for Thursday, and then some more for Monday. So hopefully you'll get a good start with these videos, and then we'll be able to get some good stuff done in class in the coming days. So hope you're doing well. Stay warm, stay safe, and I'll see you soon.